This is Taipei 101.
Taiwan's record-breaking skyscraper.
Incredibly, it's 1/3 taller than the Empire State Building.
And cost $1.75 billion to build. But Taipei 101 not only stands in a typhoon hotspot, but right beside an active earthquake fault line. It couldn't exist without the surprising engineering connections hidden deep within its design. A racing yacht.
I can't believe the speed of this thing.
A birdcage.
That didn't last long at all.
A steam pump. A safety belt. And a sports car.
So, what's all that got to do with one of the world's tallest buildings? We're about to find out.
I'm on a journey to explore some of the inspirations behind Taiwan's extraordinary skyscraper. In 2004, Taipei 101 topped the record books, reaching 509 meters.
Everything to do with Taipei 101 is big. Very, very big, whichever way you look at it. But what made modern skyscrapers like Taipei 101 possible? Bizarrely, inspiration is thought to have come from a birdcage.
Less than 5 generations ago, skyscrapers like these weren't possible. Engineers feared really tall wood and masonry structures would collapse under their own weight. So the question is,
who thought of making buildings with metal frames, and why?
Rewind to Chicago, 1871. The city is on fire. The inferno rages for 36 hours, killing over 300 people and destroying 17,500 buildings. The ruins reveal the cause. 3 months of drought turn the timber buildings into tinderboxes. As a result, the city bans wood construction. But Chicago continues to grow fast. And with land at a premium, architects search for new ways to build tall. The result, an engineering epiphany for architect William LeBaron Jenney.
The story goes that his wife had been reading a book, and she put it on top of the birdcage while she greeted him. When William LeBaron Jenney walked in, he saw the heavy book resting on top of the birdcage, and he had one of those life-changing moments.
He had the idea that buildings could be built around metal cages. Today, it may seem like any bird brain could come up with the idea of building with metal frames, but Jenney's innovation was inspired.
He realized that if he bolted horizontal beams to the upright columns and transferred the dead weight of the walls to a metal framework, he'd create not only a lighter structure, but one strong enough to support multiple stories, one on top of another.
I want to see for myself the kind of forces that a cage braced with beams can withstand. So I need some cages that I could test.
In order to find out just what a brainwave LeBaron Jenney's idea was, I've come to a workshop that has, amongst other things, a 25-ton crusher on hand. Say these represent LeBaron Jenney's columns. What I want to do is see how much vertical load they can take. That's weight to you and me. First without and then with bracing.
Structural engineer Brenda Marsh has set up an experiment to find out how much downforce it'll take to crush my metal towers.
So Brenda, I know this is all about sort of bracing or beams, but how are we going to show that? How's it going to work?
Yeah, what we're going to do is we're going to take this sample here that has some columns with no beams in it whatsoever, and we're gonna stick it in a press over there until it breaks.
What am I doing?
You're gonna operate the machine.
Okay, that's a mistake. Right, I'll do that. You better put that in the business end of it. So I need to lift the ram thing up. Apparently it's this lever. Yeah.
Okay, now what I want you to do, Richard, is lower the plate down a little bit. Don't apply the pressure yet. There you go. Okay, stop. We need to put some safety goggles on.
Oh, okay. Of course we do.
Make sure we're at a safe distance.
That'll protect us. Right, so here comes your vertical loading.
Okay.
Applying it now.
The crusher can exert 23 tons of downward force, the weight of a locomotive.
Yeah, oh, there we go.
Oh,
you can see the columns starting to buckle.
No, it's not.
There we go. The whole thing's starting to sway now. You can see.
It's
fantastic. Look at that.
And let's go on. That didn't last long at all.
Almost immediately, the tower gives way.
And that's it. It's failed.
This is what worried the early engineers, a structure like a skyscraper collapsing under its own weight.
That would be bad in a building, wouldn't it?
That would be very bad. We design buildings so they don't do that.
Okay. Right. We're all set to do that again with structure number 2. Now, this is the new one.
This is the new one.
I can see it's got more bits on it, but what are the key points? What makes it so special?
Right. What we've done on this one is we've taken what we had in the original structure.
So that's these 4 columns.
These columns, yes. Yeah. And we've added in some beams here.
That's these.
These, yes. The original structure, when it failed, the columns tended to bend outward. So what we want to do is hold those in place to stiffen up the columns.
So that means they're all 4 working together then, effectively, rather than bending and bowing?
Yes.
Okay. We've got extra bits on as well. What are these bits?
We do. What we've done is in an original building, you would have walls or something else that keep everything in place. So we're simulating that in this structure with the cross bracing.
Okay, so for the purposes of this experiment, then this is the important bit, these beams across here.
Can Jenny's tiny horizontal beams help the tower stand any greater downforce?
Okay, here we go. You watch the structure, I'm going to keep an eye on the gauge.
All right.
Straight away, that's what we were on before. 20. That's twice what it took before.
I can hear it creaking a little bit.
Okay, I'm going to
but the
increase
columns
it.
are still holding.
Increasing it now.
The crusher piles on the pressure. It's just like adding multiple stories to a tower as you build taller and taller.
25. That's going.
Oh, there we go. Started to buckle.
I've broken your clever one. But it did a lot better. I mean, it was 2.5 times stronger.
And that's exactly what we wanted to show, is that you brace off the columns and it can take a whole lot more loads.
Can I say something, though? Because I mean, instinct tells me now, tie it together, it'll work. Why?
Well, it's obvious now because we've seen it. It happens all the time. But before anyone ever thought of it, it's not the obvious solution.
Using his inspired idea, LeBaron Jenny builds the first modern skyscraper. The Chicago Home Insurance Building, completed in 1885, supports its entire 10 stories on a metal frame.
So, thanks to a birdcage and some smart thinking, the great-great-grandfather of this monster tower was born. That's how the structural engineers could build this and all its record-breaking 101 floors. But it's more remarkable than just scale. This giant stands right beside an earthquake fault line and in one of the world's most active typhoon zones. Not an ideal spot for a megatower.
Taipei 101 is the world's tallest building under such extreme threat from tropical storms and seismic activity.
So how do you build a structure that can cope with wild winds and earthquakes? And what's that got to do with bamboo and sailboats?
Taipei 101 stands like a beacon in Taiwan's bustling capital. But this city of over 2.5 million people sits right beside a ring of fault lines. And around once every decade, there's an earthquake.
In September 1999, 2,192 were killed, 8,735 seriously injured, and 100,000 left homeless by a quake.
A 12-story hotel here in Taipei City is completely destroyed. Building a 101-story skyscraper on the same fault line should be a recipe for disaster. The designers have to find a solution. Tests in earthquake simulators reveal that a building must be strong and yet flexible to avoid collapse in a quake. This is the contradiction that Taipei 101's engineers must overcome.
When you build one of the tallest structures in the world in the middle of a notorious earthquake hotspot, how do you make it strong enough to stay standing, but flexible enough to withstand the potentially disastrous effects of a seismic shock?
The award-winning Taiwanese architect of Taipei 101, C.P. Wang, found inspiration for his solution in nature. Specifically, his nation's long-standing connections with bamboo.
Well, CP, what can possibly be the connection between an immense structure like Taipei 101 and bamboo? I mean, it's not made of bamboo, is it?
No, it's not made of bamboo, of course, but in a lot of ways it's like bamboo.
How?
I think bamboo is a plant that doesn't look very strong, but it has this nature of elastic. It may bend a little bit, but it doesn't break.
Bamboo is a giant, fast-growing grass. The secret of its strength and flexibility is its internal shape. Bamboo grows in hollow, jointed sections like a series of solid-ended tubes. These are separated by partitions that help reinforce the stem. Inspired by nature's solution, Wang designs giant steel trusses to connect across the columns at every 8th floor on Taipei 101. This bamboo-inspired design must meet strict seismic targets. The owners required Taipei 101 to withstand the most powerful earthquake expected to hit the city within a 2,500-year cycle. But nature tests C.P. Wang's design even before it's complete. In 2002, an earthquake strikes. Shockwaves tear across the island. Taipei 101 shakes violently. Anything not firmly attached crashes to the streets below. Dislodged construction cranes tragically take 5 lives. But Taipei 101 stands firm and construction resumes. 2 years later, the completed megatower is crowned the world's tallest building. But by designing a structure to withstand quakes, Wang creates a new challenge. Tall buildings sway in high winds and even risk collapse in extreme storms.
And Taipei 101 is no exception. In fact, it's not just windy, it's smack bang in the middle of a typhoon hotspot.
Typhoons, Asian hurricanes, can batter Taiwan 3 or 4 times a year. In 2007, 160-kilometer winds kill 9 and cause $100 million of destruction. To keep Taipei 101 standing in a superstorm, C.P. Wang turns to an engineering solution developed 3,500 years ago. To discover this ancient engineering secret, I'm meeting Ken Maschke from the company that helped design Taipei 101. Ken wants me to try sailing, but not in an ordinary sailboat.
Ken.
Hey, Richard.
Hi, how you
Come
doing?
on board.
It's narrow, light, and has no keel sticking down into the water for stability. So how can it stay upright against the wind? This extra hull, one of two, is the engineering connection this craft shares with Taipei 101, and why Ken's got me on a sailboat.
Now it's got me working.
These clever devices are called outriggers.
There it goes.
They keep a sailboat stable in high winds.
Look at that.
Before we hoist sail, Ken explains the basic principle of the outriggers.
If you stand with your feet together and I shove on you, you're likely to fall over. If you spread your legs, it's going to be a lot tougher. Now, the same thing, in essence, is what we've done here. We spread out the distance between which the force acts.
The idea of outriggers goes back 3,500 years to the Polynesians. Using them meant the early mariners could paddle or sail fast and stay stable.
I just hope these outriggers work as well for me today. Looks a bit cold in there.
With sails up and stabilizers out, it's time to see if we can push Ken's theory to the limit.
I can't believe the speed of this thing.
Today, using outriggers like these, yachts can sail across the Atlantic in just 4 days.
Can this go over? Yeah. Would you mind awfully if it didn't? When it works, it really works. I can see how these outriggers work on a boat, but the same theory on a building. How?
The outriggers are part of the wind-resisting system, which includes a central core that's very stiff, but not stiff enough by itself. So we add these outrigger trusses to transfer force out to the exterior columns, like the pontoon that you're standing on right now. We can take the outrigger idea and apply it all the way up the building. So actually in Taipei 101, we have outriggers every 8 floors.
With a building as big as Taipei 101, every structural challenge is supersized, especially when working with the construction world's favorite material, concrete. Every floor on Taipei 101, including the 101st, is concrete. To pump concrete that high requires a super pump that has its origins in the 17th century. Rewind 300 years. The English mining industry is in trouble. The deep mines are flooding, and the man and horse-powered pumps available can't drain water fast enough. The mines are going under. Inside this modest building sits the machine that saved the day and kicked off the Industrial Revolution. It is the result of a stroke of genius from an inventive preacher and ironmonger, Thomas Newcomen.
This is Newcomen's Nodding Donkey, the first piston-powered pump.
And the first really practical engine for pumping water. Newcomen's idea was to harness the power of the pressure difference created by a vacuum. He used it to move a piston.
It works on the vacuum created by the steam when it's condensed. It works on the principle that steam occupies, say, this much space, but when you cool it and turn it back to water, it occupies a fraction of that space. So this, under here is the water, the tank, and under that is the heat. Heating it up in the boiler as steam up into that big cylinder, which is the piston. That pipe goes in to the bottom of the piston, sends the cold water in, that condenses the steam, and suddenly that huge volume of steam is reduced to just a tiny volume of water. And then atmospheric pressure outside on top of the piston is greater than the pressure inside, and it's got no choice. The piston has to come down, drawing the beam that way to do its work. Then it's counterbalanced, so it just pulls the piston back up to the top. More steam in, condenses it again, draws it back down. They were very clever.
Throughout the rest of the 18th century, Newcomen's invention drains countless minds, helping fuel the Industrial Revolution. 24 years after his death in 1753, the first Newcomen-style pump crosses the Atlantic to begin draining a copper mine in New Jersey. Fast forward 2.5 centuries to the offspring of Newcomen's engine. These powerful piston pumps use a vacuum and mega pressures to deliver concrete skyward and into the record books.
In August 2003, a world record was broken, just up there. It was the highest anyone had ever pumped concrete on a building. It had to be raised 101 floors from down there.
A pipe filled with concrete this high weighs well over 13 tons, and pumping it takes technology Newcomen could only dream about. Pumping concrete is big business, and as buildings get higher, the technology to power it to the top gets more sophisticated.
This is the business end of a pipe network that extended over 440 metres that way.
A chain of interconnected pipes stretch to reach the high floors. On Taipei 101, the pump sits near the base of the building, and the rooftop lies 4.5 football fields above. The concrete is kept flowing by a super pump. Meet the 12-cylinder, 419 kilowatt Deutz diesel engine.
This is the heart of the operation. Literally, it's the pump that keeps the construction alive. The moving parts in here made it possible to pump the concrete even to the highest floors.
A column of concrete must be kept flowing, or the mix will separate, or even worse, set. To keep a constant flow, the pump operates 2 pistons. One sucks while the other blows. A simple vacuum, like Newcomen's, pulls the liquid concrete in. Then the huge diesel engine generates hydraulic pressure to push it out. It's Newcomen's ideas, just hundreds of times more pressure for a much weightier task. I want to see what kind of pressures the Taipei 101 pumping world record used. So pump specialist Phil Suri devises a pressure demo that will blast my weight in concrete.
It's difficult to get your head around the kind of power and pressure that modern pumps can generate using those old techniques. So rather than just talk numbers about it all, we've come up with a rather clever way of demonstrating very graphically what that power can do. We're going to use pressure to move some concrete, but we're going to do it in a rather different way.
Using a concrete missile as heavy as me, Phil and his team are going to demonstrate what 100 bar of pressure can do. 1 bar, named after the Greek word for weight, is about 1 kilogram per square centimetre, or roughly the atmospheric pressure all around us. I pump my car tyres to 3 times that, 3 bar, and that seems like a lot.
It's a firing cable.
Huh? That's a cable to fire it, that's a trigger.
Right. That's
what I said, you trip over it.
Well, sorry.
I'm sorry.
But this will give me an idea of what?
Of what 100 bar of force is capable of doing. Taipei Tower, the pump that we used there was capable of 200 bar pumping pressure. This is only capable of 100 bar.
So your pumps
roughly half.
Your pumps can generate twice the pressure this.
Exactly. Yep.
And you're just telling me that because you're proud of your pump. That's what that is.
Yes, I am.
Yes, you
yes,
are.
I am.
This is a first for me, obviously. I've never seen a chunk of concrete my weight fired from a cannon. Phil is keen to see how far his concrete missile will go. The safety team are keen to make sure no one is on the receiving end.
Fire.
Wow.
So that's half the pressure on a lump of concrete the same weight as me.
Yep.
That's...
You're what, about 140 pounds?
Yeah, 64 kilos.
Okay, 10 stone, okay.
Have we got to go and get that thing
Yeah,
now?
let's do it.
Crikey.
The launcher blasts my concrete twin well over 90 meters. The top of Taipei 101 is 4 times that distance, straight up. And the record-breaking concrete column was 220 times heavier than me. I now understand the amazing pressures Phil's pumps achieve, sending concrete to the 101st floor of the Taipei Tower.
It's buried itself.
It's buried itself, yeah. It's quite impressive, look at it. 106 paces.
The mechanical pump has come a long way from Newcomen's wheezing steam engine. That's how they got concrete to the top. But how do you transport people to such heights safely and quickly? Which brings me to elevators and my next connection.
Whatever type of transport you're using, including elevators, there's a problem with going faster. You've got to be able to stop faster too. Higher speeds mean more braking loads. More loads mean more heat. So how do you provide a braking system that can work without overheating and risking a fire? And what's that got to do with a sports car?
Being big and tall like Taipei 101 means lots of elevators. In total, 67 elevators are needed to keep the 10,000 people that Taipei 101 is designed for on the move. 34 are even double-deckers. But for tourists wanting a flying visit to the sky-high viewing gallery, these regular elevators aren't fast enough. The challenge is whisking a visitor like me directly to the 89th floor, super quick, but super safe.
This is the answer. The world's most technologically advanced elevator. Well, obviously this is a model. The real thing's bigger, so you can get in it.
Digitally controlled, it has a pressurized aerodynamic capsule with shake reduction and even earthquake sensing. The designers say it also goes really fast. I want to know how fast.
This elevator, one of a pair, has been officially certified by the Guinness Book of World Records as the fastest elevator in the world. And they've given it to me to play with. So, they reckon it can do the next 84 floors in 37 seconds. Ellie, when you're ready, if you would, thank you. In your own time, go. As soon as we start moving, I'll start the clock. Go. I think we've started moving. There's no noise. There's a fan. Apparently the whole lift is pressurized like an aircraft to help stop your ears from popping. Talking of aircraft, this actually accelerates vertically more rapidly than a commercial passenger airliner taking off. And my ears are now popping. Right, we're 20 seconds in, 25. There's no sense that we're going faster than the city speed limit. We're breaking the speed limit. If we did this horizontally through the streets, we'd be in trouble. There's no noise. And that's it. And that was under 37 seconds, and this is the top.
The high-speed elevator launched me at over 64 kilometers an hour, almost half a kilometer into the sky. It's a long way up and a frighteningly long way down. If the elevator cables give way, it's an 84-floor drop with only the emergency brakes between you and the basement. In extreme events like this, metal brakes overheat and can fail. To hold Taipei 101's super elevators, the engineers needed a material that performs consistently, even when things get seriously hot.
It's an engineering line of thought that owes a lot to the automotive industry.
This is a high-performance Porsche Boxster S and my next connection. Porsche was one of the first car companies to experiment with alternatives to metal brake discs. The material that performed consistently at extreme temperatures was ceramic. Their tests report the ceramic disc brakes don't get as hot as metal and can even grip better the hotter they get. I want to check out the difference in performance between metal and ceramic brake discs for myself. So I'm meeting Craig Dawson, a motorsport engineering expert.
So, Craig, what are you doing?
Well, basically, I'm trying to get a benchmark for both the disc temperatures at the moment on the two cars.
These two cars are completely identical in every way, apart from the brakes.
That's correct. The yellow car has a traditional cast iron disc, like every modern day road car. The red car has what is known as a ceramic disc.
The ceramic compound that makes up these brake discs is usually silicon carbide or silicon nitride. It's baked at extremely high temperatures to form a heat-resistant material.
Why is heat such an issue in brake discs?
Well, with a cast iron disc, it can get to the point where it gets too hot. It begins to not work as well. The friction that it actually produces goes down.
So the pads can't grip as well on the disc and it doesn't work as well.
That's absolutely
too
right.
Much heat.
And there's double trouble when metal brakes overheat. Not only do they stop gripping as well, but if they fail to dissipate the heat, they can set fire to what's around them, as this very extreme example from the world of motor racing shows.
We have flames!
Not good for emergency brakes in an out-of-control elevator.
Almost the opposite applies with the ceramic brakes. It needs heat to get them to work in the first place, but they can go to a higher temperature as well.
So how are we, with just these two cars and that, going to show all of that?
Well, basically, you're going to perform a series of repeated stops, which are going to build the brake temperature up.
Here I go. 5 laps.
The first test, drive very fast, then hard on the brakes 20 times over 5 laps. Reckon I can manage that. The idea is to build up the brake temperature so I can feel if their performance changes as the heat increases. To gauge the temperature, we're using a camera that turns heat into visible light. The reds are hotter than the blue colours. White means it's getting serious. Craig also wants to see how quickly they lose their heat. A lack of heat loss is what can build catastrophic temperatures in metal discs.
I can smell brakes. I don't know if that's good scientifically.
627.
Okay.
When I pull in, Craig immediately checks the surface temperature of each brake disc. The readings on the front discs are well over 300 degrees centigrade. They're still functional, but as hot as the inside of a jet engine.
290.
Craig will take a further series of readings to check the rate of cooling. Thinking back, the brakes did begin to feel different once they'd got very hot, but still perfectly safe. Now it's time to take the ceramics for a spin. How will they perform? To begin with, everything seemed the same. The ceramics get white hot on the heat camera with my multiple braking. But then I notice a difference. The brakes feel really sharp each time I use them, even as they heat up. Every brake is as good as the first. When I pull in, Craig gets an immediate result.
31.
His first temperature reading on the ceramics is lower than the metal. They stayed cooler.
And did you notice any difference in the actual braking performance itself?
Yeah, they clearly weren't being as affected by the heat that was being put into them, and it felt each time I braked again, fresh.
So every time it felt more consistent, basically?
Yeah, exactly. They do pong a bit. So what have we got? What have we learned?
Well, basically, the ceramic brakes didn't get as hot as the actual iron brakes. They were dissipating the heat better whilst you were using them out on the track. When you stopped here, the temperature wasn't as high.
So they'd already lost some?
Yeah, absolutely. And what we've then seen from the temperature results is that they have lost that heat that they had when you stopped more quickly as well.
From a driver's point of view, these ceramic brakes also inspire confidence. The harder I work them, the better they feel. In the end, they stay cooler and lose heat quicker, reducing the risk of fire. This concept of using fireproof and heat-resistant ceramics for vehicles took off last century. Rewind to 1981. The first flight of NASA's shuttle is the culmination of a decade of research into heat-resistant materials. The problem is protecting the craft from re-entry temperatures capable of melting the aluminium body. Using a compound based on sand, aerospace engineers Lockheed Martin develop a new silica ceramic insulation. This forms the basis of the shuttle's heat tiles. A ceramic tile can heat to over 648 degrees centigrade on one side and stay cool enough to touch on the other. In really extreme situations, the tiles can withstand temperatures of over 1600 degrees centigrade. That's hot enough to melt rock. Heat-resistant ceramics are now well and truly proven, with their origins in rocket science and a track record in performance car brakes. On Taipei 101, they are the engineer's choice for brakes to halt a runaway high-speed elevator.
This is mission control for Taipei 101, where they monitor everything and everyone.
One full section just monitors all the elevators, including the state-of-the-art ceramic emergency brakes. Should the cables snap on the high-speed elevator, the emergency brakes will activate. 2 silicon nitride ceramic pads will grip a steel safety runner. The pads will withstand almost 1000 degrees centigrade. That's as hot as molten lava. The elevator brakes will hold 22 tons, speeding at 76.5 kilometers within 40 meters, less than half a football field, thanks to ceramics.
And that's what connects a sports car with stopping the fastest elevators in the world. But for me, the most surprising thing about Taipei 101 connects your car's seatbelts with stopping diners up on the 85th floor spilling their soup when the high winds hit.
The threat of tropical storms hangs over Taipei 101. It's not fear of collapse, but a delicate issue of customer comfort. The typhoons that blast through the city of Taipei mean driving rain and 160km/h winds slam against Taipei 101, and it feels it.
You see, a tall building like this is prone to bend in the wind. Remember the bamboo, flexibility and all that. Now, some flexibility in a tall building is a good thing. That is difficult to avoid. But too much, and it can give the people inside it motion sickness. When I asked the engineers what a typhoon might feel like in a tall building, they said, try eating soup on a bus. So I did.
Before Taipei 101 was built, it had to overcome the problem all flexible buildings face, swaying back and forth in high winds.
And like any structure, it has a natural frequency. And in this case, one complete cycle of swaying motion from here to here and back again takes about 7 seconds. Now, for customers in the restaurant, that would be like sitting on board a bus that every 3.5 seconds accelerates and then brakes. And that's the delicate problem I'm talking about. At the top of the Taipei Tower in a typhoon, you wouldn't just spill your soup, you'd probably see your whole lunch again.
The building's accelerations or movements can be plotted. This is uncomfortable. The designers of Taipei 101 must slow down the acceleration and deceleration, smoothing the rate of change to avoid motion sickness.
But how on earth do you stop a building over 0.5 kilometre high from picking up a nauseating sway in strong winds? This is how. The world's largest and heaviest damper, suspended between the 92nd and 87th floors on 16 huge steel cables.
Heavier than 3 jumbo jets, the giant ball will swing like a pendulum. The swinging counteracts the building's sway. It uses a property that all objects have.
It's called inertia.
If something is stationary, it wants to stay still. If it's moving, it wants to carry on. The desire of an object to keep doing what it's doing is inertia at work. Back in the 1950s, a researcher at Cornell University encountered the destructive side of inertia. His name was Hugh de Haven. After surviving a serious air crash, de Haven was motivated to study collisions. As surprising as it may sound today, back then, the common belief was that you were better off being thrown free in a car crash. De Haven realized the damage was done as passengers fly loose and impact their surroundings, and that inertia was the culprit. But restraining them would protect them. In 1951, Hugh de Haven files a patent for the 3-point seatbelt, and car passenger safety leaps forwards. 2 decades later, the inertia reel safety belt is introduced, initially by Volvo and Ford. It leaves you free to move around, only locking under sudden movements. It uses the very same property of inertia that Hugh de Haven realized caused injury. Inside an inertia seatbelt sits a heavy steel ball. When a car is in a collision, the inertia of the ball means it will move independently. The moving ball hits an arm that pushes up and triggers a process that locks the belt. Inertia is also harnessed in the giant 600-ton steel ball suspended at the top of Taipei 101. When the building sways, it swings like a giant pendulum. It then pushes against oil-filled shock absorbers or dampers that dissipate the sway. I want to check out the damper for myself, so I have permission to go into a construction area underneath it. It feels a bit like caving, except I'm in a tunnel over 80 stories up.
Wow! Here it is, the heart of it.
6 meters in diameter and made up of 41 separate steel plates. Only now do I get a sense of what a radical and inspired idea it is.
Suddenly, now I see it, I understand much better about how it works. This massive ball, this weight, sits here in the middle of the building, and as the building starts to move, at first the ball resists that movement. Then it starts to move, but that's where these come into play, and they're kind of like the shock absorbers on your car, only massive. And as the ball moves, these absorb the energy, they soak it up. And all of this is happening. Hundreds of tons of steel swinging about, 80, 90 stories up.
C.P. Wang, the architect of Taipei 101, has his own demo of the damper at work. So I went to meet him at the top of his award-winning building.
When wind hits the building really moves. Yeah. And it starts doing all that for a long time. It makes people uncomfortable working in the building. So what we have designed is this. If you would please take that down.
Okay. And this is more...
Replace this with this. Yeah, the purpose
this has got a ball in it.
This is our damper, actually the heart of the building.
Wang explains his metal ball in this demonstration is in an oil-filled tube. This best represents the oil-filled shock absorbers attached to the giant damper.
So I'll mount that in. So this is now with your damper in.
Now the wind is blowing again, and...
Wow. So it doesn't stop it moving, but once it started moving, it takes the violence out of the movement. It doesn't accelerate or slow down as quickly. It's a more gentle feeling. I suppose what it's doing is giving you a better ride up here, isn't it?
Buildings are for people to use, so if we cannot make the people comfortable, we don't have a good building.
On the 3rd of October 2005, Typhoon Long Wang blasts hurricane-force winds across Taiwan and presents the damper system with its first serious test. This film shows the ball in action as the 110 km/h winds blow that day. As it begins to swing, the giant oil-filled cylinders take up the energy from 500 tons of swinging steel. This extraordinary footage, filmed on a cell phone, reveals the ball damping 545,000 tons of skyscraper as she sways in the typhoon. After 3 hours, the winds abate, leaving Taipei 101 to face another day. So, thanks to scientists from the past understanding inertia, today anyone can enjoy soup in a storm at the top of one of the world's tallest buildings.
Looking down, watching the bustle of daily life on Taipei's city streets, it's hard to comprehend the incredible feats of design and engineering that went into making this extraordinary tower possible.
Taipei 101 reaches skyward thanks to a birdcage. It's built to beat earthquake and typhoon with inspiration from bamboo and ancient outriggers. It uses Industrial Revolution-style piston power for world record concrete pumping. It calls on high-tech ceramics to stop the world's fastest elevators. And is inspired by the inertia seatbelt to have storm-beating stability. Taipei 101's exceptional engineering connections mean Taiwan's record-breaking tower is one of the modern world's most spectacular construction icons.
From down here, there's just no getting away from the size, the sheer presence of Taipei 101. Now, where's my moped? There was a grey one like that, but not, no, that's, oh, that's, excuse me, is that, no, that's not mine. Why didn't I get a yellow one I could spot?